Okay. Cool. So, we're going to go ahead and start looking at some of the content from Chapter 1. Okay, so I have a question for you. What do you think of when you hear statistics? Sports. Sure. Do they use them in sports? Okay. Sure. Sports? Somehow? Sure. What else? What do you think of when you hear statistics? Or what is statistics? Any ideas?
Math.
It's math. There are some mathematicians who would have to have an argument with you about that. Okay, we don't get a lot of respect from mathematicians sometimes as statisticians, but that's okay. Okay, I'm comfortable with myself, so. What else? What is statistics?
Like percentage.
Percentages can be statistics. Sure.
Like odds. Like what are the odds or something?
Sure. You could deal with odds in statistics. Some statisticians deal a lot with odds. Sure. Anything else?
Gambling.
Yeah, a lot of statisticians work very hard to make sure that casinos make some money. Yeah. Although most of those games are pretty much set now, but yeah, sure. Somebody had to come up with them. Okay. What else? Statistics.
Collecting data.
Collecting data, yeah. Data is a really important part of statistics. All right. Without data, it's pretty hard to make any sort of informed decisions. Okay. So statistics is definitely about collecting data. Where have you ever seen statistics being used? Personally, you've probably seen it in a lot of places.
The weather.
What's that?
The weather.
The weather. You think the weather uses statistics?
They use odds. Yeah.
I think you're right, yeah.
Yeah.
Yeah. You are. Yeah. So the weather actually, yeah. Weather forecasts are all about statistics, okay? It's using data that's gathered from their surroundings along with trends from the past. There's a lot of model building that goes into creating weather forecasts, even though personally, I think that's got to be like the easiest job in the world. Especially to be, I feel like being a meteorologist in the Tri-Cities has got to be like the easiest job ever, right?
You don't have to have a meteorology degree to be a meteorologist.
There you go, see? But I'm thinking you just look at what the weather was yesterday and you just say it's going to be like that today. That's pretty much the Tri-Cities. So not very much variation.
The weather service sends them they basically just send it to them. They just have to put it on the slide.
Yeah, so most of the work is done for them. So I'm thinking that'd be a pretty sweet gig. But I'm okay where I am. What else? Who else? Where else do you see statistics used?
Politics.
Sure. In politics? How is it used in politics?
What states are voting which way.
Okay, so we do a lot of polling to try to figure out how politics are going to fall out at the election. That's a great example because that's one of those things you don't actually know how. You can have an idea of how it's going to turn out, but you don't really know how an election will occur until you actually show up on polling day. So we use it to try to predict elections, but politicians also use them. So how do politicians use statistics? How would you use statistics if you were a politician?
Well, you try and predict which regions are going to vote the most for you, and then you can figure out where to campaign.
Yeah, politicians very interested in geographical trends, demographic trends, right? It tells them where they should target their messages and target their advertising, things like that. And that's not unique to politicians. So who else uses statistics like that? Who else do you imagine uses statistics in that kind of...
The military.
The military? How so? They probably do. I don't know.
Well, because if you know where the enemy's at, then you can go there. If there's a trend that they're going to go this way, then clearly you want to go that way too.
Yeah.
Or maybe you want to go the other way.
It's true. And there's a lot of risk assessment involved in those types of operations. In fact, there's an entire field of probability specifically devoted to game theory, which is sort of some of the basis for military actions and military strategy. The idea is when you have two competing entities, and you're both trying to inflict as much damage on each other, so you can use it in sports or chess or any sort of game. It's called game theory, right? Anyways, yeah, sure. What else?
Maybe stores.
Stores?
Yeah.
Like who? I can think of one big one. Yeah, Walmart. I'm thinking Amazon, right? Have when you're like, that one time you looked up something on Amazon and then 5 months later you're getting advertisements for it on Google or Facebook, right?
That crowdsourcing.
Yeah, it's like that one time I looked up, I don't know, a stuffed animal for my kid, and now I'm getting like advertisements for Winnie the Pooh all the time, that kind of stuff. Yeah, big time. It's because they're trying to use data to direct their advertisements, get you to buy more, try to throw things at you that they think you might buy. Sure. Okay, statistics are used a lot. Anywhere else?
Healthcare.
Yes, big time in healthcare. Absolutely. A lot of ways that it's used, specifically within healthcare, the insurance industry, right? How do you think your premium is calculated when you go to get health insurance for yourself or your family? Okay, it's entirely database, right?
Probability of how you're going to die.
Yeah, actually, I mean it's an entire field. They're called actuaries, right? You guys ever see Fight Club? Right? Wasn't it Edward Norton's character at the beginning? He's sitting on the plane, and the plane's like falling apart, and he's like imagining all the ways he could die, right? Because he's an actuary, and that's what actuaries do. They calculate the risk of you dying, right? It's actually pretty morbid. But someone has to do it, right? Because they figure out, how many ways could you get hurt? What's the likelihood? If you get hurt, how much is it going to cost us to pay out on your claims, right? Someone's got to do that, and that's how they calculate your premiums, because they also have to stay in business, all right? But also within healthcare, I worked for a while with an insurance company, and they were data mining for like Medicaid fraud or Medicare fraud, right? So looking for abnormal claim aberrations in the claim data, trying to find clinics that were, basically fabricating Medicaid or Medicare fraud. They were making claims that didn't actually exist, right? So we use statistics a lot in healthcare. Anything else? Think about it. Yeah, they use them a lot in sports as well. So that's one place you mentioned earlier. But in sports, they do actually use them. So you might actually be surprised just how much statisticians play a part in sports strategy. Most major league professional teams have statisticians on their staff. Okay, and based on how a team plays, how your opponent plays, they will change their strategies to try to maximize their likelihood of scoring points or inflicting damage or whatever. Yeah, absolutely. They also record a lot of statistics just for players, right? But they're also used for strategy as well. So, yeah.
Everybody uses statistics.
Everybody, all. That makes us feel so important as statisticians. Yeah, no, really though. We do all use statistics in some ways. Okay, so pretty broad field and pretty applicable across the spectrum. If you're looking for job security for the next 100 years, you could become a statistician because everybody wants a statistician. So I'm sure that's what you guys are all gunning for, right? To become statisticians.
Oh, yeah.
Yeah. But anyways, if you want a guaranteed job, become a statistician because you'll have a job for the next forever. Okay? Until the computers get smart enough to take away our jobs, we're in good shape. All right? They're getting close. Okay. So let's look at an example of how you might use statistics. So at CBC, we enroll, about 7,400 students. It's give or take every year. It might be more or less this year right now. I don't know. Anyways, so let's say that recently we took a sample of 150 students. And what we're trying to do is we're trying to determine what % of students are planning on pursuing education beyond CBC. So after you get your associate's degree or certificate, whatever you're here for, do you plan to go to some other educational institution and take more classes or pursue some higher degree or some alternate degree? Okay. So of the 150 that were sampled, we found that 68% of students had some plans for further education beyond CBC. What do you think here? What's our population that we're interested in as the surveyor or the person taking this data? Yeah, and in fact, so who are we really looking, who are we trying to look at here? Students, right? CBC students? Are we interested in some of the students? Are we interested in all the students? Are we interested in... So we viewed a sample, right? Okay, so we viewed a sample. But do you think that's the only people we're interested in is only those 150 people?
No, this is 400.
Right, yeah. In fact, really, we're probably interested in all of our CBC students, right? Now, do you want to be the person that's tasked with talking to every single CBC student? I don't want that job. Okay.
Job security.
What's that?
It's taking forever. It's job security.
Yeah, and you don't want the job. Is it even probably really possible? Do you think you could possibly track down every single CBC student? No, because even if you could find them, do you think they're all going to answer you? Right? And people drop out, people add, right? People disappear, you know, whatever, okay? I mean, like, not in a morbid way. I mean, people just, we can't find them anymore, okay? They move away and they don't tell anybody. I don't know, whatever, okay? Don't worry, it's not dangerous to attend CBC, okay? We don't have, like, a high rate of disappearance on campus. Okay, not like that, but... So what do you think? So they took a sample of 150 people. 68% of them said, yeah, well, I'm going to take some classes after CBC. Do you think 68% of all CBC students plan to pursue education based on this? Exactly 68%? Probably not. Maybe not exactly, right? But do you think it's maybe close to that?
Probably.
Why?
Because it's an average of a decent sized amount of the students.
Yeah, so we talked to a lot of people, right? And so is if you talk about the entire population, is it going to be exactly 68%? Probably not, but it's probably going to be close, unless you just somehow manage to get 150 students that are not representative of CBC. I mean, I don't know how you do that, but you could probably imagine ways, right? Okay. Okay. So this is getting at this idea of what we call population in the sample. Okay. So the population, this is the set of all individuals of interest. All right. That's your population. And hopefully you can read my writing. So it's a set of all individuals of interest. Now the problem with this, the problem with the population is that usually it's not actually observable. Right? Typically, for whatever reason, there's really no way we can actually talk to everybody in your population. I'm not convinced that there's any way you could possibly get a hold of every single CBC student. I just don't think it's possible. Okay? And even if you could, by the time you do that, the population's probably changed. All right? So it's not really possible. So instead what we do in statistics is we take a sample. Okay? And the sample is a subset of the population which you actually observe. By the way, if my definitions don't exactly match the book, sorry. It's okay, though. I don't expect you to memorize definitions word for word. Okay? Observe. I can guarantee you that's not exactly what the book says. Mostly because I kind of just made it up. But that is what the sample is. I didn't make up the concept of sample. Yeah. So you have some population. You can't actually observe the entire thing. So what do? You take some subset that you can get your hands on, and then you observe those people. All right? Okay. So in that particular example that we just looked at, right, then what would be the population and what would be the sample?
Population is 7,400.
Yeah. The 7,400 CBC students. Or you could just think of all of them, right? All CBC students. And then what's the actual sample?
The 150 students.
Yeah, the 150 students who were observed. Yeah. All right. So the population is everybody you wish you could see if you had it your way. Like if you could freeze time, right? And just like stop everybody and say, okay, here we go. I'm going to go talk to everyone. But unfortunately can't do that, so then you take a smaller sample. All right? So far, so good? Okay. The first few weeks of this class is not going to feel like a math class. Or the first week, it's not going to feel like a math class at all. Okay. But we'll get to do some math later. All right? For better or for worse, we will get there. Okay, so within population and sample, we also have this distinction between what we call a parameter and what we call a statistic. Okay, so a parameter is a value which describes the population. So it's some description of the population. It could be a percentage of the population. It could be some average of the population. But the problem with that is that typically this is unknown, right? If I can't actually observe every CBC student, could I possibly know exactly what percent of those students are going to move on to education after CBC? I can't, right? So parameters, just like the population, we're interested in that. Okay, that's a very meaningful number. What percent of CBC students are going to pursue education beyond CBC? Very meaningful to administration, to faculty, to whoever, the state or whatever, I don't know. It's interesting to someone. Problem is you can't actually observe it. So what you can observe, though, is a statistic, okay? And a statistic is a value which describes not the population, but maybe, what do you think? A sample. No. Okay. So the way it's, I don't know if it's coincidental or not, but right, so parameter, population, statistic, sample, right? Okay. So statistic is some value which tells you something about your sample. It could be, it's typically a numerical value. I'm not sure it has to be. We do observe values that are non-numerical. We'll talk about that today. But typically it's numerical. All right? So you have parameters that talk about your population. Statistics would talk about your sample. So if you go back to that example we just looked at, the one with the CBC students, the statistics is a little easier to identify. What is the statistic here? Yeah, the statistic here is the 68% of the sample, right? Which will, whatever, you don't have to write all this down, but pursue academics beyond CBC. Right, so that's the statistic, because that 68% only refers to your sample. It says something about that group of people you observed. But what do you think the actual parameter here is that we are interested in observing if we could? What's the parameter? What do you think these people were trying to estimate or trying to get an idea of? Yeah, it's the percent of all students who will go beyond CBC. Right. So this is what we wish we could do. Of course, in reality, that actual number is just a little bit unknown. Okay, we just don't know for sure. But if we could, it'd be cool. Instead, all we really have to work with is our statistic. All right? So population versus sample, parameter versus statistic. All right, so far so good? Cool. Moving. Okay. Typically, we split statistics into two different categories. The first is what we call descriptive statistics. And the second is what's referred to as inferential statistics. Okay. One is typically more useful than the other in practical applications. So let's figure out what they mean. Descriptive versus inferential. Based on their names, any guesses what the difference is?
One's a guess and one's a description.
That's true. That's what an inference is, right? It's go to an educated guess. So descriptive statistics, these are basically values which describe something about a sample. So statistics right, these are basically descriptive statistics are just reports on what you saw, right? So I took a sample, I talked to 150 people, 68% of them are going to go pursue some academic pursuits after CBC. That is a descriptive statistic. All you did is tell me what you saw, okay? Which is interesting enough, but that's typically not really our goal as statisticians. Our goal is actually to make some inferential, basically guess. So inferential statistics is usually an attempt to use statistics to make, I'll just say, educated guesses about the population. Okay. So there's a difference here. So if you're taking a poll, say, you're trying to predict the outcome of an upcoming election or something, right? So you can take a poll and you can actually observe what percent of the people you talk to are going to vote for candidate X and who's going to vote for candidate Y. But can you really be sure who's actually going to win on election day? Not completely, right? But you could make a pretty educated guess maybe based on your statistics. So if you see a percentage that's really high in favor of one candidate, then maybe you would make the inference that that candidate's actually going to go to win the election. Okay, that would be an inference. You don't know for sure, but you're using the data you saw to make that guess. Okay, so this is inferential. I mean, this is basically where we want to be, but it's going to take us a while to get to some really good inferential statistics. But this is kind of our big goal, is ultimately getting to making some really good inferences. Okay. All right. So if you're thinking about this example we were just looking at with the students, as stated from what they said, does this appear to be an example of descriptive or inferential statistics? The way with what I reported here. So if we just look at, say, the 68% of students, would that be an example of descriptive statistic or an inferential statistic?
I'm going to say inferential the way it's worded.
This one right here. So this found at 68% of students. Maybe I should have included something there. I mean, I guess when I was writing that, I was thinking it was 68% of the 150 students.
Oh, well, then it's descriptive.
Yeah, so the way I meant it to be was descriptive. Because as far as we know, I mean, they just took a sample and they're telling us what they saw. But basically, what if a researcher reads this and says they claim that more than half of CBC students are going to pursue education beyond CBC? What would that be? Inferential. Does that actually seem like a decent inference based on the data they saw?
Yeah.
Probably. More than half would be more than 50%. In our sample, the percentage was pretty high. That probably seems like a pretty safe guess, right? You know, would you be willing to say that more than 2/3? Would you? What is 2/3? 67%? I don't know. Why would you hesitate to say that?
That's a small window of error.
Yeah, I mean, maybe we just got lucky and we happened to get a pretty decent chunk of students who were going to go on beyond CBC, right? We're going to talk about that a lot more later. It's like, where do you draw the line? You know, how far are you willing to extrapolate your sample results to your population? And what kind of errors could you experience by doing that? But that would be an inferential step. You're actually taking the data and trying to say something about the population. In this case, I think this is a pretty safe bet, probably. With 150 students and that high of a percent, probably a pretty safe bet. Okay? Any questions about that? Everybody feel good? Good. All right. So this is basically the general process of statistics that we go through. Typically, what we first do is we try to identify an objective, right? That's basically what question needs answered, right? And this usually has to do with, what sort of parameter are we looking for, okay? Does that look like English?
I mean, it looks like it.
It looks like it. Yeah, that one's not very, I need to write a little slower. So identify the example. What are you actually trying to answer? What's the parameter that you're trying to get at, right? What value are you really looking for? Okay. Once you have a good idea of what you're looking for, then you're going to go collect your data, right? That's when you're going to go take a sample. We're going to talk a little bit more about good ways and bad ways to take data, collect data. Okay. Then from there, you're going to describe the data, right? That's the descriptive step. And then from there, you're going to make inferential statements, right? So here's where you see statistics. And then the inferential step, you're going to try to make sort of your best guess about the population. Okay? I think these are kind of your book breaks it down in these 4 steps. It's a pretty good overview. All right? I think I usually always draw as a picture. Did I put that slide on here? Yeah, I put it on here. Everybody okay? Can I move on? No? Not yet. Maybe. I'm moving soon. You can always get these slides offline too. The big picture of statistics, right? So the idea is you have some population, right? The problem is it's unobservable. Okay? So from that population, what do? We take a sample. Okay? And from that sample, we're going to calculate statistics. Okay? And then what we're going to do is we're going to use those statistics to basically make inference about our parameters, because those parameters are what describe our population. Okay? So it's kind of like we're trying to say things about this world over here, parameters and populations, but you can't actually observe it all because your population is too big or changes too often or whatever. And so instead we have to work over in this world, right? The best we can do is take good samples and calculate statistics and hope that those statistics are good enough, educated enough guesses about parameters, right? And so this is basically, this is what statisticians do, right? This is all we do. The problem is that you can imagine, based on what your population is or what kind of values you're trying to estimate about your population, this can get pretty tricky. How do you take a sample? Which statistics should you calculate, right? What kind of problems can you run into when you're dealing with a small subset of the population? So it can get complicated, but this is kind of the big picture. Yeah? So if it sounds fun, you too can participate in the big picture of statistics, right? I'm going to make the hard sell. By the time you get done here, everybody's going to want to be a statistician. Probably not. That's okay, though. All right. Okay. So you were sitting here. We're going to spend a lot of time at the beginning talking about sampling and statistics. That's going to be basically like the first 3 chapters in this book. It's all this stuff. Then we're going to build up some stuff about probability and other fun stuff that's going to help us finally make this leap into inferential statistics. So the course is kind of split in half. The first half is really over here, and the last half is where we're really trying to make this step and try to start making inference. Okay. So we'll start out with taking samples. The first thing you got to figure out is is what kind of data, what kind of values are you actually interested in collecting. And we basically break data into two categories, and those categories are categorical data. And sometimes you'll hear categorical data called qualitative data. I don't like calling it qualitative data because I don't like saying qualitative and quantitative at the same time because I always get them mixed up and confused. You probably have better diction than me, so maybe you don't have that problem. But I like categorical. It's better for me. I'm also biased. That's my first statistic. Most statistics textbooks refer to them as categorical. So anyways, categorical data, or categorical variables. I should add a line here. Okay. These are characteristics which group individuals into categories. That's why I call it categorical. Or you could think of it's qualities of individuals. Okay. So some things about categorical data. It's usually non-numerical. Can you think of a categorical or qualitative variable about a person? What would be a non-numerical quality of a person?
Eye color.
Sure. So things like a person's eye color, that is a non-numerical value. But it says something. It lumps you into a category, right? What else? Anything else you know? What are some other categorical variables you can think of?
Hair color.
Sure. Since we're talking about the colors of our features. So eye color, hair color. Sure. What else?
Gender.
Sure. Gender is a categorical variable, non-numerical. It just groups you into a category. What else?
Their race.
Sure. Something like your ethnicity, your race, right? Okay. Things like that. Things of that nature. Okay. So, of course, we could take data about non-human things, right? So you could take your data could be, automotive parts or something like that, right? There's qualitative variables there and quantitative. So quantitative is the flip side of that. So for quantitative data, these are always numerical. And I like to include that have some natural ordering. And what I mean by that is that the fact that something is labeled 1, 2, and 3 has a meaning. Okay, meaning that 1, 2, or 3, like if you're talking about dollars, right? 1, 2, and $3 have a natural ordering. 1 is different than 2 is different than 3 in the same way. Each one is more than the next. Okay, because I think in the next slide we'll see that you can make numerical values which are categorical if the numbers don't actually denote any type of order. All right. Okay. So some examples of quantitative data. So what's a quantitative feature of you?
Height.
Sure. Okay. Your height, your age. Sorry, I'm getting kind of low on the board, but shots are kind of like. Okay, what else? Anything else you can think of?
Weight.
Sure. Okay. These are numerical values. They have a natural ordering, right? Okay. If someone's 18 and someone's 23 and someone's 30, right? That means you're older. Okay. Height means you're taller. Okay. So let's see some examples here. We already did this one. Gender. What is it? We label that one. Categorical, right? It's non-numerical. Just groups you in a category. The way I think about it actually, well, I'll tell you in a second. What about temperature? Temperature, you go outside, you measure the degrees. Quantitative. One way I kind of always make the determination is I asked the question, does it make sense to average? Right? Does it make sense to average out people's genders? Like add up everybody's genders and divide by what? I don't know. Right? It doesn't make any sense to average genders. Does it make sense to average temperatures? Sure. You can think of a lot of reasons why you want to average temperatures, right? How about number of days per week you work?
Quantitative.
Also quantitative. Sure. Makes sense to average. Where's zip code?
I'm gonna go with categorical.
Yeah, so this is one of those examples where it's a numerical value, but I don't think it's quantitative. Right? You think so?
It has to have a natural order, right?
Not really.
You can't average a zip code.
Yeah, I mean, does it really make any sense to average zip codes? I mean, they sort of have some meaning, I think, right? Because they're kind of give you a general, like, I don't know. It seems like lower zip codes are on the East Coast and higher zip codes are on the West Coast in general, right? In general. But does it make sense to, like, average zip codes at all? Right? If you average the zip code of Pasco with the zip code of Seattle, do you get the zip code of Ellensburg or something? Right? It doesn't make any sense. Okay? So it's really is, even though it's numerical, it's really just categorical. All it really does is tell you where that person is. Can you think of another one like that?
Area code.
Yeah, I was thinking area code, I don't know about license plate.
How about a phone number?
But area code, yeah. Like area code on your phone number. Okay? So I'll say also, an area code is even more so because area codes are all over the place. It really doesn't have a lot of basis on location. Doesn't seem like. Okay? So, yeah. So the ordering doesn't really matter. It doesn't really tell you anything about anything except for where they are. All right? Cool. Make sense? All right. Easy enough. Too bad you can't average zip codes. I wish. I don't know why. It just seems like it'd be cool. All right. Types of data. We have so these are within qualitative. I should actually write this. So not within qualitative, within quantitative. See, this is why I don't do quantitative, qualitative. Within quantitative, not categorical, we also differentiate between whether or not we're dealing with discrete data or whether or not we're dealing with continuous data. So when we talk about discrete data, what we're saying is we're talking about values which can only occur on a fixed interval. And typically that fixed interval is integers. Or counting numbers. Okay? So it's like things that you can only have a whole of. You can't have fractional or decimal portions of. So can you guys think of a variable which would be discrete? Like you can't have a fraction of it.
Number of people in a room.
Sure, right? So number of students or people, because I'm in here, I'm a person too. Number of people in a room, right? Because you either say you're in or out, right? You can't have like 2 1/3 of a person in a room, okay? If you did, you just tell the other person, dude, get in the door, get out, okay? We're having class, let's go. What else? Anything else?
Number of bullets in a gun.
Okay, sure. I assume it would be difficult to have a fraction of a bullet in a gun. I don't know anything about guns, to be honest, but I'll take your word for it. Sure. Okay. Sure. Number of cars in a household or something, or a parking lot. I'll just say household because that's a more manageable number. But yeah, number of cars per household, like the number of cars that are registered to you or to your address or something like that, right? Has to be fixed. You can't register like 3/4 of a car and be like, whoa, dude, give me a break. My car doesn't run, you know? They're not going to do that. You either have to register it or not register it, okay? The state doesn't care. Okay, so that's discrete variables. I just spent a lot of room taking that up. But continuous is kind of the flip side of that, where values can occur on an infinite spectrum or on infinite continuum or whatever. I don't know how to say that. I don't know. I feel like I can't use the word continuum to describe continuous. But basically like fractional decimal values. Can you guys think of some things that we might consider continuous variables? So you can't, they don't just occur on like fixed numbers.
Like height.
Yeah, like your height is actually really on a continuum because really if you get really nitty gritty, I mean, none of us are probably exactly the same height. If you take it out to like, you know, one billionth of an inch or something like that, we're all different. Okay. Height, yeah, I would just call continuous. What else?
Your age.
Yeah, time. Anything dealing with like time or length, we're going to treat those as continuous variables. Money, right? We typically treat money. So even on a day-to-day basis, we round it off to cents. In reality, especially when you're dealing with like stock markets and stuff, those things trade so fast that it makes sense to treat them like continuous variables. All right? So time, length, money, those are all things we treat continuously. All right? So just looking at a couple examples. What time does this class get out?
12:30.
Okay. Is that clock right? What time is it? Where's my phone?
That clock's like 1
I have no idea where my phone is.
12:08.
It's 12:18. All right. Cool. Wonder where my phone went. Huh? You know what? I'm so glad I did not go to college I'm glad I went to college before smartphones. Because it would be way too distracting to me. So I didn't have a smartphone when I was in college, so it was really easy. No, I don't care where my phone is actually because I'm due for an upgrade. So if it disappears, I'll just get a new one. But it'll give me a good excuse. Anyways, I think I do know where it is, but we'll see. Okay, anyways. Number of heads obtained if you flip a coin 10 times. What would that be? Discrete or continuous? That's definitely discrete. Because it's going to happen, 4 or 5 or 6 or no times. But it can't happen 1.37 times. All right? Number of miles you can drive on a tank of gas.
Continuous.
That says continuous. You could get to some pretty fine decimal points on that measurement, right? Depending on how fine your odometer is or whatever. How about the value of a stock at 2 o'clock in the afternoon? Let's say continuous. Probably is going to get reported maybe to the nearest cent, but in reality, it's trading pretty fast. What about the number of eggs you purchase at the grocery store?
Discrete.
I would say it's probably discrete. I don't know. Unless you're going to buy broken eggs or egg beaters or something. Like, how many eggs went into this egg beater carton? I don't know. 31.7? I don't know. Okay, but anyways, yeah. I don't buy egg beaters, so I don't know. Okay. Yeah, makes sense? Pretty straightforward? Cool. So far, so good. It's going to be great. I forgot about this. Your book spent some time talking about levels of measurement, so I threw it in here anyways. And now I'm trying to remember if I remember the definitions of this stuff. So nominal measure. So there's different levels of measurements. A nominal level of measurement is basically just think of it as categorical. I think the way they give it in the book is it's kind of like it gives a name nominal, right? So anything you're measuring that's categorical variable, we say that's at the nominal level of measurement. Ordinal is more like qualitative data. Okay. So numerical. And then interval and ratio, these are actually both examples of ordinal measurement, but they have one main distinction, is that they're both on a spectrum, where 2 is more than 1 is more or whatever. But in interval measurement, 0 doesn't necessarily mean like nothing is there. Whereas in ratio, 0 means literally nothing. And this will make more sense probably with the examples I'm about to give you. Okay? So an interval, it's like there is an interval and we measure it on a spectrum, but just because you have 0 as your measurement doesn't mean that there's nothing there. Whereas ratio it is. It's like you start at 0 and you have nothing and then you start adding things. Okay? So let's see. Maybe you should just look at the book. It has a way better definition than I just gave you, but it'll make sense in a second. Okay, I promise. Okay, so gender is what type of measurement? What level? Nominal. So here's where it's interesting. What about temperature? So temperature is ordinal. Now, is it an example of interval or ratio? Why interval? Yeah, does 0 degrees mean there is no temperature? No, it doesn't, right? It's like altitude, right? With regards to sea level. Just because you're at 0 feet above sea level, does that mean like you don't exist or like there is no height? Like you know what I mean? Right? So temperature is ordinal, but it's on an interval. What about number of days per week that you work? Ordinal. And it is ratio. Because if you work 0 days per week, that means you did not work. Right? That's a lack of work. If you worked 4 days per week, you work twice as long as someone who worked 2 days per week. Right? The ratio holds. And 0 means nothing. How about your letter grade on a report card? I don't know. I don't think we give letter grades here, but maybe in high school. Other colleges do. All right. Make sense? Yeah. Sure.
So ordinal is also considered categorical and qualitative?
No. Ordinal is just for qualitative.
Didn't you say qualitative could be also considered as part of categorical?
No, that's quantitative.
Oh! Wait, let's time out. Back up. What?
So in notes you said categorical could also be considered
Qualitative, yeah.
So ordinal is also considered qualitative.
Quantitative.
Okay.
Did I write it wrong?
Yeah, you put qualitative.
Ah, dang. See, that's why I hate using that word. Boom, boom, boom. What am I doing? No, go back. Erase it. Yeah, good catch. Quantitative.
Go ahead and give me extra credit for that. No, I'm just kidding.
All right. Quantitative. Okay. Yeah. There we go. What's I got? Okay. So all right. So let's actually I just want to stop there because that's a good place to pick up tomorrow. But what I would like you to do is that if you're not registered for my math lab, definitely get registered tonight and go ahead and do that orientation assignment. It'd be really nice if you started on the first homework. That'd be really great. And bring questions to class tomorrow.
So is that due tomorrow?
The orientation assignment is due on Thursday. Today is Tuesday.
So like what's the whole thing about homework? Is it homework every night? Also the chapters that we cover? Or
No, the homework is all front loaded and it's all due on the exam.
okay.
but we're covering the material as we go. Yeah.